Welcome back. We've covered a lot of ground in Module 3. In Session 3.1, we built the complete architecture of a prompt, understanding its 6 components, the system versus user divide, and the 26 research-based principles that separate precise prompting from casual instruction. In Session 3.2, we confronted hallucinations head-on, understanding why they're inevitable at an architectural level and how to engineer a layered defense that reduces them by up to 96%. Today, we're moving up the ladder. We're going beyond the anatomy of a single prompt and into the paradigms that define how you use prompting to solve genuinely complex problems. These are the techniques that separate practitioners who understand prompting at a surface level from those who can direct AI reasoning with precision. Zero-shot prompting, few-shot prompting, chain of thought, self-consistency, tree of thoughts. These aren't just tricks, they're distinct cognitive strategies, each suited to a different class of problem. By the end of this session, you'll have a comprehensive decision framework for choosing the right technique for any task you face. Let's climb the ladder.
Before we dive into specific techniques, we need to understand the foundational capability that makes all of them possible: in-context learning, or ICL. In-context learning is a model's ability to adapt its behavior to a new task purely from examples provided in the prompt itself. No fine-tuning, no weight updates, no retraining. The model's parameters remain completely unchanged. The learning happens at runtime, in the context window, and it evaporates entirely when the conversation ends. This is a remarkable and somewhat counterintuitive capability. These models weren't trained on your specific task. They weren't optimized for your exact domain or your particular output format. And yet, when you show them examples of what you want, input-output pairs that demonstrate the pattern, they generalize from those demonstrations and apply the pattern to new inputs with surprising accuracy. The reason this works goes back to the training process. These models have been exposed to such a vast and diverse corpus of human-generated content that they've internalized a general capacity for pattern recognition and task generalization. When you provide examples in the prompt, you're not teaching them something entirely new, you're activating and orienting a capability that already exists in their weights. Understanding ICL as the underlying mechanism is important because it frames every prompting technique we'll cover today as a variation on the same fundamental idea. The more precisely you communicate your intent through examples, instructions, and reasoning structure, the more accurately the model can execute it.
Prompting paradigms we'll cover are organized by a simple but powerful dimension: shots. The number of shots is simply the number of labeled examples you provide in the prompt before asking your actual question. Zero shot means you provide no examples at all. You give the model a task description and a query, and you rely entirely on what it already knows from training. This is the simplest form of prompting, and when it works, which it often does for common, well-defined tasks, it's also the most efficient. One shot means you provide exactly one example, one input-output pair that demonstrates what you want. Even a single example can dramatically shift the model's behavior, particularly when the task has an unusual format or domain-specific vocabulary. Few shot means you provide multiple examples, typically somewhere between 2 and 10. You're essentially constructing a mini training set in line, showing the model a range of cases that illustrate the pattern you expect. This is the most powerful and flexible technique for complex or specialized tasks. The SHOT framework gives you a vocabulary for thinking about the cost-benefit trade-off in every prompting decision. More shots generally means higher accuracy for complex tasks, but it also consumes more context window, that finite resource where everything the model can see at once lives. The art of prompting is calibrating the right level of example richness for the task at hand, without wasting tokens on examples that don't add signal.
Zero-shot prompting is exactly what it sounds like. You give the model a task and ask it to complete it with no examples, no demonstrations, no templates to follow, just your instruction and the question. And for a surprising range of tasks, it works remarkably well. Basic sentiment classification, Is this review positive or negative? Is a zero-shot task. Simple translation between common languages, summarizing a clearly structured document, answering factual questions within the model's training distribution. For these kinds of tasks, the model's pre-training has already encoded everything it needs to succeed. The mental model for when zero-shot is appropriate: zero-shot works when you can give the model everything it needs to know except the examples. If you can describe the task completely and unambiguously in plain language, and if that task type is well represented in the model's training data, zero-shot is often the right starting point. It's also the right starting point for cost and speed reasons. Zero-shot prompts are shorter, they consume fewer tokens, generate faster responses, and cost less per call. In production systems handling high volumes, that efficiency compounds. Where zero-shot breaks down is on tasks that are highly specialized, that have unusual output formats, or that require the model to understand an implicit standard it hasn't encountered before. If you ask for a specific type of structured output and the model keeps getting the format wrong, or if you're working in a domain with unusual conventions, that's your signal to move up to few-shot. Zero-shot is your first attempt, not your only tool.
Few-shot prompting is where prompting becomes genuinely powerful for professional applications. By providing labeled demonstrations before your query, input-output pairs that show the model exactly what a correct answer looks like in your context, you dramatically expand the range of tasks the model can execute reliably. The structure is straightforward. You write 2, 4, or 6 examples in a consistent format. Here's an input, here's the corresponding output I want. Then you present your actual query in the same format, and the model completes it by continuing the demonstrated pattern. What makes few-shot transformative is its applicability to complex and domain-specific problems. Suppose you're classifying customer support tickets into a proprietary taxonomy that doesn't exist in standard training data. Zero-shot will produce inconsistent results because the model has no prior exposure to your specific categories. But give it 5 examples of correctly labeled tickets, and it will generalize to new ones with high accuracy, because it has internalized the classification pattern from your examples. The same principle applies to specialized writing styles, proprietary data formats, domain-specific analyses, and any task where your desired output follows a convention the model couldn't have learned from general training data alone. Few-shot prompting is also remarkably robust. The model doesn't need perfect examples, it needs representative ones. Examples that cover the range of inputs it will encounter, examples that reflect the edge cases you care about, and examples that are consistently formatted so the pattern is unambiguous. Get those 3 properties right, and few-shot becomes one of the most reliable tools in your production prompting toolkit.
Once you've decided to use few-shot prompting, the next question is, how many examples and which ones? The research here gives us clear guidance. On quantity, 3 to 8 examples is the sweet spot for the vast majority of production use cases. Below 3, you may not have enough diversity to reliably communicate the pattern. Above 8, you start hitting diminishing returns. Each additional example adds less signal while consuming more of your context window. The sweet spot is providing enough examples to make the pattern unambiguous, but no more. More important than quantity is quality and diversity. This is the principle that practitioners often underestimate. A set of 5 diverse, high-quality examples will dramatically outperform a set of 10 redundant ones. Why? Because redundant examples don't teach the model anything new. They just reinforce a pattern it already captured from the first few. Diverse examples, by contrast, cover more of the input space and give the model a clearer picture of how the pattern generalizes across different situations. Correctness matters enormously. Counterintuitively, research has shown that even incorrect labels in few-shot examples, where the input-output pair is wrong, can still partially guide model behavior because the format signal is preserved. But deliberately providing wrong examples will poison your results. Every example should represent exactly the output quality and format you expect in production. One final principle: your examples should reflect the actual distribution of inputs your system will encounter. If your real queries skew toward a particular subtype, include examples of that subtype.
The model generalizes from what it sees, so make sure what it sees is representative.
In 2022, a team at Google Brain published a paper that changed how researchers thought about prompting. The technique they described was chain of thought prompting, and its implications were immediate and far-reaching. The core insight was simple. Instead of asking the model for a direct answer to a complex problem, show it examples where the reasoning process is spelled out step by step, and then ask it to reason through your question the same way. Before chain of thought, the standard approach was to provide input-output examples where the output was just the final answer. Chain of thought changed the output in the examples to include the intermediate reasoning steps, the work shown between problem and solution. And that change in example structure triggered a qualitatively different kind of model behavior. When the model sees reasoning chains in the examples, it learns to generate reasoning chains of its own. Instead of pattern matching to a final answer, it produces a sequence of intermediate steps, decomposing the problem, working through each component, and arriving at a conclusion through a chain of explicit logic. The results on complex reasoning benchmarks were dramatic. Tasks involving multi-step arithmetic, common sense reasoning, and symbolic logic saw accuracy improvements that standard few-shot prompting couldn't come close to matching. The reason is intuitive. Complex problems have multiple failure points, and a model that reasons step by step can catch and correct errors at each step, rather than attempting one giant leap from question to answer and hoping it lands correctly.
One of the most remarkable discoveries in the chain of thought literature is how little it takes to activate reasoning behavior in large models. In a 2022 paper by Kojima et al., researchers demonstrated zero-shot chain of thought, the ability to trigger step-by-step reasoning without any examples at all. The method? Simply appending the phrase, "Let's think step by step," to the prompt. That's it. No examples, no elaborate instructions, 4 words that activate a qualitatively different reasoning mode. The results were striking. On a standard math benchmark, the GSM-8K, the baseline zero-shot accuracy was 17.7%. Adding "Let's think step by step" pushed that number to 78.7%. That is a 4.5 times improvement from a 4-word addition to the prompt. Why does such a simple phrase have such a large effect? The answer lies in training data. Large language models have been trained on enormous quantities of text that includes worked examples, academic solutions, tutoring conversations, and problem-solving walkthroughs. The phrase, "Let's think step by step," or close variants of it, frequently appears in that training data as a signal that careful, structured reasoning is about to follow. When the model encounters that phrase, it's activating a pattern it's seen thousands of times. Slow down, decompose, reason explicitly. The phrase is essentially a runtime instruction that redirects the model from pattern matching mode into reasoning mode. Variants work too. Let's work through this carefully. Think through each step. Reason step by step before answering. The specific phrasing matters less than the signal it sends. This is one of the highest leverage individual techniques in prompt engineering, worth internalizing deeply.
Chain of thought works, but why exactly? Understanding the mechanism makes you a better practitioner because it tells you when the technique will and won't be effective. The answer is emergence. Reasoning, not just pattern completion, but genuine multi-step logical reasoning, is an emergent property of large language models. It doesn't appear in small models. It doesn't appear in medium models. It emerges relatively suddenly in models above approximately 100 billion parameters. Emergence in neural networks refers to capabilities that appear discontinuously as model scale increases, behaviors that are essentially absent at smaller scales and then appear to switch on as the model crosses certain size thresholds. Reasoning is one of the most important of these emergent capabilities. The reason scale enables reasoning is a matter of capacity. During training, these very large models absorbed not just facts, but the logical structure of how those facts relate. They've processed mathematical proofs, scientific arguments, legal reasoning, philosophical analysis. At sufficient scale, the model doesn't just memorize conclusions, it internalizes the inferential patterns that connect premises to conclusions. When you prompt a large model to think step by step, you're activating those latent inferential patterns. You're essentially saying, don't skip to the end, show the work. And because the model has enough capacity to store and execute multi-step reasoning chains, it can do so, producing solutions that are traceable, verifiable, and significantly more accurate than single-step completions. This is why zero-shot COT works on frontier models, but produces limited gains on smaller distilled models. The capability has to exist in the weights before a prompt can activate it. Scale is the prerequisite.
Chain of thought improves reasoning, but what about high-stakes decisions where a single reasoning chain, even a good one, might still be wrong? That's the problem self-consistency solves. Self-consistency, introduced by Wang et al. In 2022, is built on a powerful intuition. If a model truly understands a problem, it should be able to arrive at the correct answer through multiple different reasoning paths. A correct conclusion is robust. It survives different approaches. A hallucinated or incorrect conclusion is fragile. It tends to appear in only some reasoning chains and not others. The technique works like this. Instead of generating one chain of thought response, you generate multiple, typically 3 to 5, sometimes more, using a non-zero temperature to introduce variation in the reasoning paths. Then, you collect the final answers across all those runs and apply majority voting. Whichever answer appears most frequently is selected as the final output. The logic is essentially ensemble reasoning. Just as ensemble methods in machine learning aggregate multiple model predictions to reduce variance and improve accuracy, self-consistency aggregates multiple reasoning chains. Errors in individual chains tend to be idiosyncratic. They appear in some chains and not others. Correct answers tend to be consistent. They appear across the majority of chains. The accuracy gains on complex benchmarks are substantial, often pushing performance well above single-chain COT. The cost is proportional. Generating 5 chains costs roughly 5 times as much as generating 1. That trade-off is worth it in high-stakes contexts, medical triage, legal analysis, complex financial modeling, where the cost of an incorrect output is orders of magnitude higher than the marginal cost of additional inference.
Self-consistency improves confidence on problems with a single correct answer. But some problems don't have a single path. They require exploration, evaluation, and strategic backtracking. For those problems, we have Tree of Thoughts. Tree of Thoughts, proposed by Yao et al. In 2023, extends chain of thought from a linear progression into a branching search. Instead of committing to one reasoning path, the model explores multiple candidate paths simultaneously, evaluates the promise of each path, and selects which paths to continue, which to prune, and when to backtrack if a path reaches a dead end. Think about how a strong chess player approaches the middle game. They don't commit to a single move sequence. They mentally explore multiple branches, evaluate the board state at different depths, eliminate dead ends, and focus their attention on the most promising lines. Tree of Bots gives a language model this same multi-path deliberation structure. The implementation involves the model generating multiple next thoughts, partial steps toward a solution, at each node in the search tree, evaluating each thought's viability, and then continuing to expand the most promising branches. If a branch leads to a contradiction or a dead end, the model backtracks to the last viable node and explores a different direction. This makes Tree of Thoughts particularly powerful for complex planning problems, multi-constraint optimization, creative tasks with many possible approaches, and any problem where the right solution requires exploring and discarding several wrong approaches before finding the right one. It's computationally expensive, potentially requiring many more model calls than standard COT, but for genuinely hard problems, it enables solution quality that linear reasoning approaches simply cannot match.
The final technique in today's toolkit is least to most prompting, and it addresses a specific failure mode that even chain of thought can struggle with, problems that are too complex to reason through in a single continuous chain. Least to most prompting, introduced by Zhou et al. In 2022, works by explicitly decomposing a hard problem into a sequence of simpler subproblems, solving them from easiest to hardest and using each answer as input to the next step. The key insight is sequential dependency. When you solve a complex multi-part problem all at once, the model has to hold the entire problem in mind while reasoning about each component, and errors in early reasoning steps can compound and propagate through the entire chain. By contrast, when you break the problem into subproblems and solve them sequentially, each step builds on a confirmed correct foundation. Error propagation is interrupted at every stage. Consider a complex legal analysis task. Rather than asking, "Analyze all relevant issues in this contract dispute," you decompose. First, identify the governing law. Then, identify the relevant clauses. Then, analyze each clause against the governing standard. Then, synthesize the findings. Each answer feeds into the next question. The model never has to solve the full complexity in one step. It climbs a ladder of progressively harder subproblems. This approach mirrors how expert human problem solvers actually work. Complex problems are rarely solved in a single flash of insight. They're solved by breaking them into manageable parts, solving each part, and assembling the components. Least to most prompting encodes that strategy directly into the prompt architecture. It's especially valuable for compositional tasks, multi-step analyses, and any problem where you can articulate a clear logical dependency between subproblems.
You now have 5 techniques in your toolkit. The critical skill is knowing which one to reach for. Let's build that decision framework explicitly. Zero Shot is your starting point for tasks that are common, clearly defined, and well represented in the model's training data. Translation, basic summarization, simple classification, answering factual questions. If Zero Shot gets you to acceptable accuracy, stop there. It's fast, cheap, and sufficient. Few Shot becomes necessary when Zero Shot produces inconsistent results, usually because the test has an unusual format, a domain-specific vocabulary, or an output structure the model hasn't seen in general training. Provide 3 to 8 high-quality, diverse examples, and you'll capture most of what you need. Zero Shot chain of thought is your go-to for logical reasoning, arithmetic, multi-step analysis, or any problem where you can feel the complexity. Just add the trigger phrase, "Let's think step by step," and let the model show its work. It costs almost nothing extra, and the accuracy gains on complex tasks are significant. Self-consistency is your reliability amplifier for high-stakes decisions. When the cost of being wrong is high, generate multiple COT chains and take the majority answer. Use it when accuracy matters more than speed or cost. Tree of Thoughts is your heavy artillery for complex planning, multi-constraint problems, and creative tasks with large solution spaces. It's computationally expensive, so reserve it for problems that genuinely require exploration and backtracking. Not every complex-sounding task actually needs this level of search. And Least to Most is your tool for compositional complexity, when a problem has a natural decomposition into sequential subproblems. If you can articulate the dependency structure of a problem, this technique will often outperform a single COT chain on the full problem. The meta principle: start simple, escalate deliberately. Don't reach for Tree of Thoughts when Zero Shot COT will solve it. Reserve your most expensive techniques for problems that genuinely require them.
You've just completed Module 3, the full arc from prompt anatomy to reliability engineering to advanced reasoning paradigms. Let's anchor what you now own. You started Module 3 understanding how to build a structurally complete prompt, the 6 components, the system user architecture, the 26 research-based principles. You then learned to engineer around the fundamental reliability challenge of AI systems. understanding hallucinations at an architectural level, and building layered defenses that bring them down by 96%. And today, you've added the Cognitive Toolkit, a set of 5 prompting paradigms that let you direct AI reasoning across the full spectrum of task complexity. These 3 layers compound: a well-structured prompt, grounded with RAG and validated by guardrails, executing a chain of thought or self-consistency reasoning strategy. That combination represents professional-grade AI usage. That's what it looks like to actually engineer with these systems rather than just use them. But prompts, as powerful as they are, only take you so far. In Module 4, we move into the next frontier, agentic AI. Agents are AI systems that don't just respond. They plan, use tools, execute multi-step workflows, and operate autonomously over extended tasks. They can search the web, write and run code, call APIs, manage files, and coordinate with other agents. Understanding how to design, deploy, and govern agentic systems is the next major capability gap between practitioners who were ahead of the curve and those who are still catching up. Module 4 will get you there. I'll see you in the next session.